General motions. Let's start this section by some concept. To determine the relative velocity of B with respect to A, the time derivative of the relative position equation is taken. And we got this equation. Vb slash A, the relative velocity of particle B with respect to A is equal to Vb minus Va, or we can show by this equation. Vb is equal Va plus Vb slash A. Va and Vb is our absolute velocity, and the Vb slash A is relative velocity of B with respect to A. Rolling motion. Look at this figure. The round object of radius r is rolling on the stationary plane surface with counterclockwise angular velocity. The velocity of point C in contact with the surface is 0, and the velocity of the center B is r times omega in the direction that shown. Angular velocity vector. Suppose that an object's axis of rotation is parallel to the z-axis, and the object is rotating in the counterclockwise direction with angular velocity omega. Then its angular velocity vector is omega k, because it's in the k direction. General plane motion. Look at this figure. Let's consider the object with current orientation A1 and B1 after a very short time period as dt. It has moved to this new location A2 and B2. As you can see, the object has both translation and rotation. The combination of both translation and rotation is known as a general plane motion. To study the general plane motion, let's focus on the motion of two arbitrary A1 and B1. First step, consider we only translation. Point A has moved its new location A2. So we can show displacement of particle A by vector dra. Also, point B1 has moved it to new location B1 prime, and the displacement of particle B is the vector dr B1 prime. And the initial relative position of particle B1 relative to particle A1 is RB slash A, and the initial relative position of particle B1 prime relative to particle A2 is RB1 prime slash A2. If you remember, during translation, the displacement for all particles in the rigid body are all the same. Therefore, the displacement of point B1 is the same as the displacement of the A1 during the first step. So, drB is equal dra. For this reason, the relative position of particle B1 prime relative to point A2 stay the same, as well as we know we can show by RB slash A, meaning both is same and this one is same. For the second step of the motion, the particle B1 prime rotates about a fixed axis that is perpendicular to this point and pass through point A2. So B1 prime is rotating about point A2. Now particle B1 has a new relative position with respect to A1, and change in its relative position is represented by drB slash A. And from vector addition, we know that the displacement of particle B from B1 to B2 is a dra plus drB slash A. And this is the equation. Now look at this equation. If we take the time derivative of this equation, we get this equation for linear velocity for any two arbitrary particles in the same rigid body that's undergoing general plane motion. It says that the absolute velocity of particle B is equal to the absolute velocity of particle A plus relative velocity of B with respect to A. As you can tell, the velocity of particle B has two contributions. VA represents the contribution from the first step of the motion, that is translation, and VB slash A represent the contribution from the second step of the motion, that is the rotation. And from what we learned before for rotation about a fixed axis, the linear velocity of any point equal to the cross product of omega and position vector with respect to the center of rotation. Therefore, for a rigid body undergoing general plane motion, the absolute linear velocity of the rigid body of particle, for example, for particle A can be determined as the absolute linear velocity of particle A and the cross product of omega, that is the angular velocity vector of, that is the angular velocity, times the RB slash A, that is the relative position vector of particle B with respect to A. Also, acceleration in plane motion we can find by this equation. Or we can say the acceleration of B can be expressed in terms of the acceleration A and the position of B relative to A and the angular velocity of the rigid body. And the angular velocity and the angular acceleration, as you remember, we show by alpha. Let's look at some examples. Bar AB is rotating a clockwise angular velocity of 10 radians per second. Point C slides on the horizontal surface. At the instant should determine the angular velocity of bar BC and the velocity of point C. Look at this figure, okay? The axis of rotation of bar AB is parallel to the z-axis. It means for omega. And the bar is rotating in the clockwise direction. So the angular velocity vector is omega AB is equal negative 10 k radian per second. Now we apply this equation and we can find or determine the velocity at point B. At bar BC, the angular velocity omega BC and also the velocity of point B and point C are unknown. The velocity of point B in previous step we find it. Now we have to find the velocity at point C. When we apply this equation, we got this one. From the problem, we know that the point C slides on the horizontal surface. So the VC in the J component is equal to 0. So from this equation, we can find the omega VC. After we replace to this equation, we can find the VC. The VC is 6 meter per second and omega VC is 5 radian per second. As you can see, the omega BC is positive. The answer is positive, is meaning the rotation is counterclockwise. Bar AB has a counterclockwise angular velocity of 10 radian per second and clockwise angular acceleration of 300 radian per second squared. What are the angular acceleration of bar BC and CD? First of all, we have to determine the velocity of the VB and VC. We know that the angular velocity of bar BC and bar AB, we can determine the velocity at point B. After that, we can determine the velocity of point C in terms of the velocity of D in this part, okay? To find the omega CD. Also obtain the velocity of C in terms of the velocity of B, in terms of the B. This is the equation. Now we have two equations. From equation 2 and equation 3, we can find the omega CD and omega BC. The omega CD is 10 radian per second and it's positive, so it's counterclockwise, and omega BC is negative, is counterclockwise. Also, we use the same sequence of steps to determine the angular acceleration. The acceleration at point B we can find by this equation because the problem given the alpha AB and also omega AB. For finding the acceleration of C, we can determine in terms of the acceleration of D. We know that we don't know the alpha CD, but we find the omega CD in previous step. We solve this one. Again, the alpha CD is still unknown. And also the acceleration of C in terms of the acceleration of B is like as this one. And from this equation, we have also alpha BC. We obtain AC by equation 5 and equation 6 because both is showing the AC. From this equation, we find the alpha BC is 100 radian per second square and alpha CD is negative 100 radian per second square.